adventurers arrived on the island, afraid of the unknown and unaware of their surroundings. They quickly observed the area and the natural beauty around them. Malik began to ponder how they arrived here, but he could not remember anything. However, the adventurers quickly discover a tablet with a video and a message on it. After uncoding the message, they learn that the only way to escape this island is through learning AP Calculus Unit 8. They click on the video and begin their mission, finding the area between curves without a calculator and with a calculator.
For our first question, it's a non-calculator question where we have to find the area between the curves. Now, to find the area, we need to look at the integral of a to b of the top function minus the bottom function dx. Now, to find a and b, we have to look at the intersection points, which is negative 2 and 7 and 2 and 7. So a is negative 2 and b is 2. Now we have to identify the top and bottom function. This curved one is f of x, which is x squared plus 3, and this flat line is g of x, which is just 7. Our top function is g of x, and our bottom function is f of x. Now that we have the bounds and the top and bottom functions identified, we can just plug in what we know, which gives us this. Then, after we get this, we can multiply by negative 1 and simplify the 7 and negative 3 together, which gives us this. Then we can take the antiderivative, which gives us this, and then after we plug in 2 and negative 2 and subtract those, it gives us 16 thirds minus negative 16 thirds, which comes out to 32 thirds, which is our answer. For our second question, we are also solving for the area between the curves, which is a calculator question this time, and we're using the same equation that we did last time. F of x is 4x squared minus 1, and g of x is negative 3x squared minus 5x. Remember, we are looking for a and b on our integral and the top and bottom function. We can plug these two right into Desmos, which gives us this. G of x is our blue function, and f of x is our red function. Then for a and b, we need to identify our intersection points, which are these two x values, and our top and bottom function. G of x is the top, and f of x is the bottom. So that gives us this. Then we can plug g of x and f of x right into our equation, which gives us this. And then when you plug this into Desmos, it gives you 1.312.
Alright, so I'm going to be going over volumes with the known cross-section for Unit 8. And firstly, we're just going to be looking at the formulas for the cross-section. So there's obviously multiple different cross-sections that you might be exposed to. So these are just the formulas that you need to memorize and you can refer to by going back to the video. Alright, so for our first example, we're going to have a cross-section that's perpendicular to our x-axis, which is a square. So we're going to first identify which our top function is, which is going to be 2x, and our bottom function, which is going to be 2x cubed. And yeah, so we also know that our intersection points for our bounds are going to be at 0 and 1. So our bottom bound is going to be 0, and our top bound is going to be 1, as that is where the functions intersect. And next, we're just going to do our top function, which is going to be 2x, I believe. Yes, 2x. So we're going to have 2x parentheses and then subtract from our bottom function, which is 2x cubed. That is our bottom function. And then we're going to go ahead and square all of that. As to determine the volume of a square cross section, all you need to do is square the whole thing, which is in the integral. Okay, so let's go ahead and plug this into Desmos so we can get our answer. So 0, 1, just top function 2x minus 2x cubed, and then make sure you guys add a dx. After in Desmos so that you can determine your answer. But yeah, that's all you need to know for this first example. That right there is going to be your right answer, 0.305 if you want to round it. All right, for our second example, we're going to not be using a square cross-section. Rather, we'll be having a semicircle cross-section. So we're going to be utilizing a different formula. But firstly, let's go ahead and plug in both of our functions. So we can obviously see that one is our top function, but next we need to identify where the functions intersect so we can determine our top bound, which is going to be 0.69336. So let's go ahead and copy and paste that into our integral. Next, what we want to do is add a pi over 8 outside the integral in front of it so that because that is going to be our formula for a semicircle. So just make sure you memorize that. And then just simply do your top function minus your bottom function. So 1 minus 3x cubed. And then we're going to go ahead and square that and then add a dx. And that right there is going to be your answer to this one. All right, here's some practice questions to hone your skills and improve in this. So pause the video and solve these.
All right, today we're going to be doing disk method. All right, so for our formula for disk method, we need to use the area of a circle, which is pi r squared. To find the radius, though, we need to subtract the lower function from the upper function. What this looks like is, when we're showing a graph, our upper function, f of x, minus our lower function, g of x, and that would equal our radius. To find the volume, though, we need to use the setup. We need to integrate it and use the setup of pi times the integral from a to b of f of x minus g of x squared dx. That squared comes from the radius squared. Example problem 1 here. Let region R be the area enclosed by the function f of x equals e to the x minus 2, the horizontal line y equals negative 4, and the vertical lines x equals 0 and x equals 3. Find the volume of the solid generator when region R is revolved around about the line y equals negative 4. You may use a calculator to round to the nearest thousandth. Alright, so we have our graph here. We can see e to the x would be our upper function, and negative 4 would be our lower function, and then our functions enclosed by that x equals 0 and x equals 3. Like I just said, our radius would equal e to the x minus 2 minus our negative 4. So when we find the volume, we plug into Desmos, pi times the integral from 0 to 3, because those are our bounds, of e to the x minus 2 minus negative 4 squared dx. And that would equal approximately 909.669. Alright, let's go to a second problem here. Let region R be the area enclosed by the function f of x equals x cubed minus 1, the horizontal line y equals negative 2, and the vertical lines x equals 0 and x equals 2. To find the volume of the solid generated when region R is revolved about the line y equals negative 2. Alright, so our upper function would be x cubed minus 1, and our lower function would be y equals negative 2. To find the radius, we're going to have to subtract those. So we have x cubed minus 1 minus that negative 2. And to find the volume, we're going to have pi times the integral from 0 to 2 of x cubed minus 1 minus negative 2 squared dx. That volume would equal 88.862 approximately. Alright, let's go to our third and final problem here. Let the region R be the area enclosed by the function f of x equals square root of x plus 1, the horizontal line y equals negative 1, and the vertical lines x equals 0 and x equals 9. Find the volume of the solid generated when the region R is revolved about the line y equals negative 1. Alright, so our upper function here would be the square root of x plus 1, and our lower function would be x equals negative 1, or y equals negative 1. find our radius, we'll have the square root of x plus 1 minus -1. To find the volume, here we're going to use the setup pi times the integral from 0 to 9 of the square root of x plus 1 minus -1 squared dx. Plug that in our calculator, and we will get volume is approximately equal to 466.527. Alright, thanks for learning disk method with me.
Hello everyone. Today I'll teach you what the washer method is in calculus. The washer method is used to find the volume of a solid created by rotating a region around an axis, but unlike disk method, it handles solids that have a hole in the middle. The volume of the solid is given by this formula: V equals pi on the range of A to B of big Rx squared minus Rx squared dx. Big Rx is the outer radius, or the distance from the axis to the outer curve. R of x is the inner radius from the axis to the inner curve, and A to B is the interval along the axis you're rotating around. You'll use the washer method when you're rotating around an axis, when there are two curves but one is closer to the axis, and when you're told to find the volume of a shape with a gap in the middle. How to do this is I would sketch the region and label the curves, decide the axis of rotation, usually an x or a y axis, set the integral using the equation stated above, and find the limits of a and b, and then evaluate the integral. Let's work through our first example. We're asked to find the volume generated by rotating the region between the curves y equals square root of x and y equals x from x equals 0 to x equals 1 around the x-axis. First, we should sketch the graph. However, on this problem, I already gave the graph in Desmos. Next, we must find our axis of rotation, which is the x-axis, so our radii must be in terms of y. Next, we must find our inner and outer radius. Our outer radius, for this case, is the square root of x, where our inner radius is just x. Now we plug it into the formula we were given above, and then we evaluate it to get pi over 6. Let's try another example, this time rotating around the y-axis. We're rotating the region bounded by y equals x and y equals square root of x from 0 to x equals 1 around the y-axis. Since we're rotating around the y-axis, we need to rewrite our functions in terms of y. For y equals x, we solve to get x equals y. For y equals square root of x, we square both sides to get x equals y squared. Next, we need to set up and find our outer radius and inner radius, where our outer radius is equal to y, and our inner radius is equal to y squared, with limits in y from y equals 0 to y equals 1. Next, we set up our integral. So we get v equals pi from 0 to 1, y squared minus y squared, that squared again, dy, which equals pi on the range from 0 to 1, y squared minus y to the 4th dy, which then we evaluate, and we get 2 pi over 15.
This information for the entire night, the adventurers quickly gear up for their escape. Sunrise is near, and according to the tablet, escape can only be made at sunrise. The adventurers use the information to locate the escape test and apply their knowledge to get the correct answer while searching their surroundings. Finally, they get the check mark and begin walking towards a new beam that is being formed nearby. They all disappear, leaving only the tablet, now glowing, in their wake.